Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 3rd, 2025, which was just yesterday. The main contribution is a new optimizer called AdaGO that keeps Muon's orthogonal update direction, but uses an AdaGrad-style scalar step size to adapt to gradient magnitudes, delivering optimal convergence rates and better accuracy than Muon and Adam in the reported tests. The paper is titled AdaGrad meets Muon, Adaptive Step Sizes for Orthogonal Updates, and the implications for model training are quite significant. Beyond the headline, the authors prove optimal rates for nonconvex problems, add only one extra scalar state, and show strong results on function regression and CFAR10. On X, a post highlights AdaGO combining AdaGrad-style steps with orthogonalized momentum, shows plots beating Muon and Adam, and attracts solid interest with about 130 likes. The previous figure highlighted overall gains, and Figure 1 now compares optimizers on the regression task. The left panel shows training loss, where the green adaptive Muon curve drops fastest and settles lowest, while Muon trails and Adam W descends slowly with larger oscillations. The right panel reports test loss, which mirrors the pattern, so generalization improves alongside training. The sharp early spikes likely reflect warm-up and step size adaptation stabilizing after the first 100 to 200 steps. Alright, the previous figure showed loss curves, and Table 1 now lists the tuned hyperparameters that produce those results. The table contrasts regression and classification settings, which matters because the learning rate and the epsilon floor control stability and speed. Adam used a fixed learning rate in each task, while Muon used a smaller fixed rate. AdaGO paired a larger base rate with a small epsilon floor, so the method could move quickly, yet remain stable when gradients dipped. So the previous table detailed settings, and Figure 2 compares optimizers on CFAR10. The left panel presents training loss over epochs, where the green AdaGO curve descends fastest and stays lowest, which indicates more efficient fitting. The right panel reports test accuracy, and AdaGO consistently edges out Muon, while both surpass Adam, so better optimization translates into stronger generalization. The early rise is steep, because the adaptive steps quickly calibrate to gradient norms. So the previous figure focused on CFAR10 accuracy, and Figure 3 contrasts gradient descent with orthogonal gradient descent across two toy setups. The left panel shows a one-layer linear network, where orthogonal gradient descent converges quickly with a moderate learning rate, but oscillates when the step is too large, which signals instability. The right panel presents a one-layer attention model, and orthogonal gradient descent achieves lower training loss than plain gradient descent for comparable steps, because orthogonalized updates avoid shrinking along already learned directions. Okay, two takeaways stand out. AdaGO preserves the orthogonal update direction while adding AdaGrad-style scalar adaptivity, and the method reaches optimal convergence rates with only one extra accumulator, which makes it practical. The broader implication is simpler, faster training that generalizes better. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.